So as we go through chapter 3, we're going to start adding more terminology. And certain terminology should make you think certain things. Just like when we said slope of the tangent line, you should think first derivative. Now when I say increasing and decreasing, you should think first derivative and potentially relative max and min, depending on what you have and what you're trying to solve for. And now we're moving to a new term called concavity, okay? Concavity. Now, concavity is what it means everywhere else in the world, all right? It is how something is shaped, all right? Concave up, right? That looks like a bowl that is sitting up. Concave down, that's like a bowl that is upside down, okay? So concave up, concave down. That should naturally create a picture in your head. And what you'll find is that you can tell based on your derivatives how something is concave. We just did a parabola. Well, if it went from decreasing to increasing, then it is concave up, right? The bowl is up, right side up. If it went from increasing to decreasing, that bowl would be down, concave down, right? And so one way you can tell concavity is first derivative, just figuring out is it increasing or decreasing. There's also another way, and that is by using the second derivative, and that is this theorem right here at the top of page 185. Let f be a function whose second derivative exists on an open interval. So obviously you have to be able to find the second derivative. If that second derivative is positive, then it is concave up. If the second derivative is negative, then it is concave down. So you find like a new set of numbers. It is no longer critical numbers, but it is numbers of your second derivative where they are 0 or undefined, pretty much is what you're looking for. And what this tells you is not where the increasing and decreasing changes, but where the concavity changes. So like you would have a critical number somewhere down here, right? Because it would go from decreasing to increasing. But concavity would change somewhere in here, where all of a sudden it's going to turn from concave up to concave down. And so these are not going to be the same numbers that you would necessarily have for first derivative. There are going to be some situations like the undefined will often follow, because where the first derivative is undefined, the second derivative will typically be undefined as well. All right, but as far as where they're equal to 0, they're not going to be the same numbers that you're looking at and the same set of numbers that you would use for increasing to decreasing. So let's look at this first example. Now, I will say you do not have to use quotient rule here, nor would I, okay? When you just have a number in the numerator or a number in the denominator, it is not quotient rule, all right? You can just rewrite it. So they want to know where it is concave up or down. So concavity should make you think second derivative, okay? So concavity, second derivative. So what I am going to do is I'm going to rewrite this function with a negative exponent. I'm going to say 6x squared plus 3 to the negative 1. That's going to be much easier than trying to use a quotient rule. So I have to first find first derivative, multiply by that negative 1, take it to the negative 2, and multiply by the derivative of the inside. So it looks like this, negative 12x, x squared plus 3 to the negative 2. Now, if I were just finding first derivative, I would rewrite this guy. But because I'm not, I'm finding second derivative, I'm going to actually leave him alone. I can do this two ways. I can do this with the product rule or with the quotient rule. Both of them are going to require chain rule when I do this. But I can do it either way. I can leave it like this and do product rule because I am doing negative 12x times x squared plus 3 to the negative 2. Or you can do it like they did in the book, rewrite it, and do quotient rule. You will get the same answer. Product rule or quotient rule will give you the same answer here, all right? So if we did product rule, the derivative of this guy is going to be negative 12. The derivative of this guy is going to be negative 2 times your 2x, that's the inside, times x squared plus 3 to the negative 3, right? Make sense? So we have negative 4x, x squared plus 3 to the negative 3. All right. So far, so good. There is a little caveat to your product rule we'll talk about when we take stuff out of it. But so derivative of the first, that's negative 12, times the second, just the way it is, that's x squared plus 3 to the negative 2. And then plus the first, that's negative 12x. Derivative of the second, that's negative 4x, x squared plus 3 to the negative 3. All right. Now, when you factor something like this, you factor out the lowest. All right, the lowest. What's my lowest exponent here?
How'd you get a negative?
Which one? So if I'm factoring out the lowest exponent, I'm actually going to factor out that negative 3 exponent. All right, so I'm going to divide out my x squared plus 3 to the negative 3, all right? When I do that, by the way, I get a negative 12 here, negative 2. If I pull out three of those, negative 3, it's like negative 2 divided by the negative 3. And remember, I subtract negative 2 minus a negative 3. So this ends up being x squared plus 3 to the first power when I pull out a negative 3. I'm dividing. So remember when you divide common bases, you subtract their exponents. So you have negative 2 minus a negative 3 there. Over here, I have negative 12x, negative 4x, that's positive 36. X squared, right? And then I pulled this entire group out. So far, so good.
Oh, this isn't even the second. I see what you did.
Wait, okay.
So now I'm going to take out 12.
So,
Or no.
I mean, oh, this should have been 48. I was already subtracting in my head. Sorry, this is 48, not 36. I already subtracted my 12. Sorry, I was moving ahead in my brain. That's 48. When you add it to that negative 12, you're going to get 36.
Okay.
I just did a step ahead in my brain. This guy's going to go in the denominator, yes, because he's a negative. So that's going to go in the denominator, x squared plus 3 to the positive 3 in the denominator. In the numerator, I have negative 12x squared and positive 48x squared. That is 36x squared. And the negative 12 times 3 is negative 36. All right? This is my second derivative. Now, you could have done quotient rule up here. You could have done derivative of the top times the bottom minus the top derivative of the bottom over the bottom squared. And you would get the same exact thing. Okay? So I have found my second derivative. Concavity says, where does this either equal 0 or where is it undefined? Undefined means the denominator would be 0. You're never going to get the denominator equal to 0 because you have something squared, which will be positive, plus 3 to a power. And that will always be positive. So it will never be undefined. We just have to worry about that numerator. And so if I were to take this numerator and set it equal to 0, that's where my whole thing is going to be 0. So take out a 36, you get x squared minus 1. Where does that equal 0? That's going to equal 0 at positive and negative 1. Everybody agree? All right. Positive and negative 1 are going to make it 0. You are going to do exactly the same thing that you would do with increasing, decreasing, but now we're using second derivative and we are finding concavity. So we're going to say from negative infinity to negative 1, from negative 1 to positive 1, and from positive 1 to infinity. And we're going to test those in our second derivative. So we want to know does this yield a positive or negative in my second derivative? All right. Let's take -2, okay? If I do -2, now I already said the bottom's always going to be positive, yes? Isn't that true? Because I'm going to square any number and add 3. So I already know that my denominator's positive. So all I really have to worry about is my numerator. If my numerator's negative, the whole thing's negative. If my numerator's positive, the whole thing's positive, right? So let's say I take a -2. Well, -2 squared minus 1 is a positive number times 36, which is positive. So this guy is going to be positive, right? Let's put 0 in there because that's a good number in between -1 and +1, right? 0 minus 1, that's negative times 36. This guy's going to be negative. And then if I put any positive number in there, bigger than 1, and subtract 1 from it, it's going to be positive, right? So this group is also positive, which means that we're not doing increasing, decreasing. This is concave up. This is concave down. And this is concave up. All right, so let's look at the graph. All right, and it's hard to tell because you don't see the whole graph here. This is gonna go kind of like that, right? Here, it's concave up. The bowl is up. This is where we have a turning point, where we go from concave up to concave down. Do you see the difference between increasing and decreasing? It's still increasing here. So your first derivative would be positive this whole way. So it changes concavity at different points than it changes increasing and decreasing, okay? And so this group here is concave down, and then this is where it starts curving back to be concave up, all right? So this, along with your increasing and decreasing your critical numbers, start to give you an even better picture of your graph, right? All right, so we're going to do second derivative because we're doing concavity. So we're going to start with our first derivative, obviously. Derivative of the top, that's 2x times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. Simplify it. At the top, those two cancel, and you end up with negative 10x over x squared minus 4 quantity squared. That's my first derivative. Second derivative. All right. Derivative of the top times the bottom. Minus, and that's going to be minus a negative, so we're just going to do plus that 10x. And then for the derivative of the bottom, you have 2 times your 2x times your x squared minus 4 to the first power. All over the bottom squared. All right. I think they pulled a 10 out. I'm not sure, but I think they did. So if you'll notice, you actually can take out one of your x squared minus 4s because it's in both groups. So this group has an x squared minus 4 and this group has an x squared minus 4. So before I start distributing and all that craziness, I'm going to cancel that out. Does everybody see that? So I'm going to go ahead and take out one of these from every group, right? And that's going to make my life a little bit easier. So I have negative 10 x squared plus 40. And then this is what? 40x squared. Oh yeah, they pulled out. And then that's over x squared minus 4 cubed. Just simplify this guy. I think they pulled a 10 out just to make it easier. So we have a 10 on the outside here. You get 3x squared plus 4 over x squared minus 4 cubed. All right. So where is this going to be equal to 0? This is my second derivative. Well, the numerator is never going to be 0. I have something squared plus a number. I'm never going to get that equal to 0, not in the real number world, right? So then I say, well, is there any place that would make the denominator 0 where it's undefined? And yes, there is. There are two numbers that would make that 0, positive and negative 2, right? So I'm going to test from negative infinity to negative 2, from negative 2 to positive 2, and from 2 to infinity in my second derivative. All right. Negative 3. Well, I already know the top's going to be positive, right? Always. So negative 3, what does that do? Well, that's going to be a positive 9 minus 4 cubed. Well, that's going to be positive, right? 0. 0 minus 4 cubed is negative, and my numerator is always positive, so this guy is going to be negative. And then 3, positive 3 is going to yield a positive again. So what does that tell me? That tells me that I have concave up, concave down, but this graph looks different than the other one. Look at the graph of this one. And so if you look at this graph, it definitely is concave up, concave down, concave up, right? But all of a sudden it looks completely different than the other graph. So what you're starting to build is you're starting to build pieces from pre-cal and calculus that help you get an even better picture of this graph. Whereas in pre-cal, you were kind of sketching just what you thought was happening. In calculus, you get a little more. So you're like, oh, I can find my vertical asymptotes. I can find my intercepts, my x-intercepts, my y-intercepts, which this one wouldn't have any x-intercepts. And then all of a sudden, this makes sense as to what's happening because I can find increasing, decreasing, I can find concavity, and all of it flows together with what a picture of my graph looks like. If C, f of C, is a point of inflection, then it's where your second derivative is equal to 0, or it's not differentiable, it's undefined, okay? So points of inflection are like the second derivative of critical points, if that makes sense. Critical points are where your first derivative are equal to 0 or undefined, right? Points of inflection are where your second derivative is equal to 0 or undefined. So that's what we have been finding. We have been finding points of inflection, points of inflection. And what you'll notice is that points of inflection can occur at these two possibilities. If you have a point of inflection, then it's where your concavity changes. So if the tangent line exists, then there is a point of inflection. And you look at the bottom of page 186 and you see the types of inflection. It goes from concave up to concave down to concave up. You see the different types of points of inflection. Concavity changes. So how do you find them? Well, you set your second derivative equal to 0 or where it's undefined, and then you determine, did my concavity change? If my concavity changed, then I have a point of inflection. All right? So there is a little note that says the definition given in this book requires that the tangent line exist at the point of inflection. Some books do not require this. So like this piecewise function that they give you. This book would say it does not have a point of inflection, even though the concavity changes. So sometimes they will not consider like the one we just did as a point of inflection because you actually don't have a tangent line there because it's undefined. Some of them will. And so you just have to pay attention to how they're defining that point of inflection, right? I typically will take it if it is a change of concavity at one of these. Let's look at example 3. Determine the points of inflection and discuss the concavity of the graph. You're going to love this one. This derivative is beautiful compared to the ones we've been doing, right? Don't you think? Please, give me these all day long.
Sarcastic because I wasn't looking at those.
All right, so look at this guy. My first derivative, we got a beautiful first derivative, right? 4x cubed minus 12x squared. Second derivative, just as easy. It's going to be 12x squared minus 24x. We find out where that equals 0 by just pulling out that 12x. We get x minus 2. So I have 2 points. It can either be at x equals 0 or x equals 2. And so I'm going to set up my intervals, negative infinity to 0, 0 to 2, 2 to infinity. And we're going to see what happens here with second derivative. Plug in a negative 1. Well, negative 1 squared is going to be a positive 12 minus 24 times a negative 1 plus, right? So that's going to be 12 plus 24. So this is going to be positive, right? Plug in a 1. Well, if I plug in a 1 here, I get 12 minus 24, which is going to be negative. And if I plug in something like a 3, I'm going to get a positive. So I'm going to get a larger number minus a smaller number there. All right. So hopefully this thing will go concave up to concave down to concave up, right?
When you're plugging the numbers back in, so you pick like a negative 1 in between negative and 0, do you plug in?
But you can see that he goes concave up, right? Concave down, concave up. All right. Second derivative test. So this is one more thing you can do with second derivatives, really. At this point, we can do a lot more, but let f be a function such that the first derivative equal to 0. All right, so that when first derivative is equal to 0, we have a critical number, right? The second derivative exists on the upper interval. If, when you plug in a critical number to your second derivative and you get a positive, you have a relative min. If you plug your critical number into your second derivative and get a positive, you get a max. I mean, a negative, you get a max. So it's opposite of what you would think. Why is that? Well, we're going to find our critical numbers. That is where my first derivative is 0, and it's where I have a turn, right? Remember, first derivative equal to 0 is where I have a turn in my roller coaster, okay? If I plug it into second derivative and I get a positive, that means it's concave up, which means my critical number is at the bottom of my bowl, which means it's a minimum. If I plug my critical number into second derivative and get a negative, it means that graph is concave down. My bowl is upside down, and my critical number is at the top of the bowl, which means it's a maximum. So while a positive says concave up, it also says minimum because you're at the bottom of the bowl. If a negative says concave down, you actually have a maximum because it's at the top of the bowl, okay? So if you are doing second derivative, you can test your critical numbers to know if you have a max or min without going back to first derivative. That's what second derivative test does for you. So let's look at this. It says find relative extrema. What we would normally do is we would say, oh, okay, first derivative, set up intervals, increasing, decreasing, right? You don't really have to do that. You can say, let's find first derivative. First derivative, that's negative 15x to the fourth plus 15x squared, all right? Let's find our critical numbers here, all right? Well, to find your critical numbers, set it equal to 0. So we're going to pull out a negative 15x squared. We're going to get an x squared minus a 1. Where does this equal 0? Well, my critical numbers will happen at negative 1, 0, and positive 1, right? Negative 15x squared gives me 0. X squared minus 1 gives me positive and negative 1. Those are my critical numbers. Now, normally to find relative extreme, you would say, okay, negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity, right? And you would test a number in between there and see if it goes from increasing to decreasing to increasing to decreasing. But that's not what we're going to do. We're going to now find second derivative. And we're going to say, what's the second derivative here? Well, the second derivative is going to be negative 60 x cubed plus 30x, all right? And you can factor out a 30x if you want to. But what we're going to do is we are now going to plug these critical numbers into my second derivative. This tells me the concavity at that point, okay? And I know at this point is the peak or the valley because those are my critical numbers. So I am going to find my second derivative, and really I just need to know if it's positive or negative. All right? Yeah, so this is x cubed. There we go. That's going to be a little better. This one's going to be a negative times the negatives, right? So this is going to be negative times negative 60 positive. So this guy's going to be positive. This is concave up. That makes more sense. 0. Test fails here. If you get 0 when you plug it in, you cannot do second derivative test, okay?
So do you do something else with it, or you just say test fails?
Yeah, test fails. You're not going to have a relative max or min typically. And when you look at this graph, you'll see the difference, all right? So if this is concave up and my point is at the turn right here, right? I have a minimum. That means negative 1 is a relative min. This guy is a relative min. He's at the bottom of a curve, right? If this is concave down and my point is at the top, this is a relative max. So while it tells you concave up, you have a min. When it tells you concave down, you have a max. And so instead of setting up intervals and going, oh, increasing to this would have been a lot of intervals. Instead of doing that, you can just plug it in.